Hi, let's get straight to this particular new chapter, which is random variables. Now, this is a very important reading because the next three chapters that we have in our quants book, they all have many of the concepts which we will study in this particular chapter. And also, let me tell you that if until this point, maybe you were afraid of quants, or maybe you did not like quants, or I would even say that you might have thought about skipping some of the chapters in quantitative analysis because you feel that this is tough. But let me tell you this, quant is a very interesting subject, and we're going to be using a lot of visual diagrams so that you understand even the difficult concepts in a much simplified way. And at the end of the session, you will change your perception. Alright, and just before we go ahead, this is our email ID, queries@vardeez.com. In case you have any queries or if you want any guidance, this is our official WhatsApp number. You can contact us any of these medium to know about the FRM pricing and plans. Okay, these are the learning objective. We're going to be talking about the probability mass function, also known as PMF. There's this cumulative distribution function, which is CDF, and we also have this probability density function, which is referred to as PDF. Now, these three concepts is something that is confusing to most of the candidates, but don't worry, I've got some diagrams, some visual representation that will help you to grasp these concepts very well. Then we have all these different learning objectives, but let's quickly get into the first learning objective now. Okay, describe and distinguish a probability mass function from a CDF. Now, before we get into this PMF and CDF, let's first understand the basics. Okay, so what is a random variable? A variable whose value is unknown, or we can say that whose outcome is unknown to us. That is when we can say that the variable is a random variable. Consider this example of stock returns. Now, can you tell me what could be the potential return on any particular stock? Will the stock go up tomorrow by 1%, by 2%, maybe 0.5%, or it can even come down to negative 1%, 2%, and so on. So we cannot be sure what could be the potential returns on any particular stock. So we can say that the returns, they can even go up, they can stay stable, they can come down, or it can take any path. So we can say this variable behaves random in nature, and that is why we say they are a random variable. Second example is a loss on a particular portfolio. We don't know what could be the potential loss that we can face on a particular portfolio. So essentially, the outcome of these losses, they are unknown to us, they behave in a random way, and that is why we again say they are a random variable. Similarly, I can say for interest rate, they can go up, they can go down, we don't know what the outcome is. And finally, when I roll a dice, I don't know what value will it land upon. I really don't know. So it's random in nature, and that is why we again say it's a random variable. So hopefully the concept of random variable is clear. Now let's understand the notations that we will be using throughout this book, and this will come in very handy. If you understand the basics and the notations very well, you will not have any confusions later. So usually we denote the random variable with this capital letter X, okay, and all the possible outcomes that the random variables can take, we denote that with the small x. Okay, so that's why I said if you look at this, the capital letter X and the small x, initially you will be confused, or initially you may have a thought process like what exactly is this? They both are very similar. The only difference is with the capital letters, and this is a small case. In statistical language, there are some notations that will actually help you. For example, so rather than writing this entire probability, we just write as this P. Similarly, I can say that rather than writing this entire statement, what is the probability that when I roll a dice that it lands on a 3? So rather than writing this entire statement, I can write this as the probability that this is the random variable, okay, and the small x is the outcome, okay. And now what is the probability that this random variable x will take on the value as 3? So this is how I can write it in a very short form, this entire statement, and still you'll be able to understand this, that the probability that the random variable x that is rolling of a die, it takes the value of 3. I hope you get the notations now. Okay, it's just a short way of writing things rather than writing the entire statement. Now oftentimes you will come across that we are talking about this distribution, we are talking about a probability distribution, and so on. So it's important that we understand what exactly do we mean by a distribution and a probability distribution, so that there is no confusion going forward. Alright, so a distribution, it describes all the possible outcomes of a random variable. Okay, on the other hand, a probability distribution, it also describes all the possible outcomes that the random variable can take along with their associated probabilities. Okay, I'm going to show you an example and that will make clear what do we mean by a probability distribution. So here we have the probability distribution of a coin toss, and over here we have rolling a dice. So if you roll a dice, what's going to be the possible outcomes? It's going to be 1, 2, 3, 4, 5, 6. So the random variable x can take all these 6 possible outcomes. So this is referred to as a distribution, okay, because it describes all the possible outcomes of a random variable. On the other hand, the distribution here for a coin toss is either heads or you can have tails. So this is the distribution, and over here we also have the probabilities associated with these possible outcomes. So I can say that when we have the probabilities as well, we can say that this is a probability distribution. Similarly, this table is also a probability distribution. So that's what do we mean by a probability distribution. I hope this is clear now. Okay, focusing our attention to the types of random variables. Yes, we do have these two different types. The very first one we have is a discrete random variable. Now here the random variable can take on only a countable number of possible outcomes. Okay, that is referred to as a discrete random variable. As an example, let's suppose we have 10 students in a class. So we can count 1, 2, 3, 4, 5 up until 10, right? Maybe we can have 40 students, maybe we can have 100 students. So something that is countable, that is what do we mean by a discrete random variable. The marks that you can score on a particular exam, that is countable, right? So that's a discrete as well. What about ratings that you get on a particular bond? Now here the ratings can be, it can be AAA, it can be B rating bond, it can be BB, so on and so forth, right? But you cannot count as a particular number, but still the outcome is observable. It doesn't go into infinity. Okay, so when the outcome is something that you can observe it, it doesn't go into infinity, we can still consider that as a discrete random variable. Okay, understand, you can only have few ratings, right? I mean, after that, let's say A, B, C, and then finally you have a junk category. It doesn't go beyond that. So I can still call the ratings on a bond as a discrete random variable. Okay, then we also have credit scores. You can have a credit score of 650, 700, 750, 850, so on and so forth, right? So that is something that is observable, you can count it, it doesn't go into infinity. That's a discrete random variable. Now the opposite of discrete, we have the second category, and that is the continuous random variable. Now what do we mean by that? A continuous random variable is a variable which can take uncountable number of possible outcome values, something that goes to infinity. You really cannot stop at a specific value. Over here we can stop at a specific value, we can have these specific numbers or these ratings, but over here there's nothing specific. Okay, so that's what do we mean by a continuous random variable. As an example, the height of an individual. Now let's say I'm 179 centimeters. Okay, but is it exactly at 179? No, I can be 179.01. I can also be 179.001. I can be also 179.00001. So basically the decimal places at the end can go to infinity. Okay, if I go ahead and if I really get into the actuality of this thing, it goes beyond 179 and possibly to infinity. So there's no one specific value that I can derive when we are in a continuous random variable. Okay, so that's what we can say, that the height or probably the weight that we have, or I will also say that returns that you get on a particular stock or a company, the returns on a calculator, we can have like up to 2 decimal places, 4 decimal places, 10 decimal places, right? But talking about it, it goes beyond 10 decimal places. It just keeps on going to let's say the return is 0.01%. I can have 0.0001%, I can have 0.00001, so on and so forth. It just goes beyond to our calculations, and that's what we mean by a continuous random variable. And it's important to note that when we are working with a continuous random variable, the probability of a specific value for a continuous random variable is 0. Okay, this is important. When we are working with continuous, you cannot stop at a particular point. So of course, if you want to find a specific value, the probability of that would be 0. Okay, we're going to be taking few examples, don't worry about that. So when we're talking about the discrete, there's also something known as the probability mass function, or referred to as PMF. Now what PMF tells us is that it shows the probabilities that the outcome of a discrete random variable x will be equal to a given number. Okay, I'm going to show you an example so that you understand this in a much better way. But for now, if I have this discrete random variable, and if I want to see what are the possible outcomes that the discrete random variables can take, then I can have a look at this PMF and I can see that. Okay, the example will come in the next slide. So PMF, it will show me all the probabilities that the outcome of the random variables will take. Okay, now the notation for the PMF is f of x. Okay, so this is how we say that. So rather than writing the probability that the random variable x is equal to x, I can write it at this way as well to refer to PMF. Okay, so f of x, that's what we say, that this is a PMF. On the other hand, if I want to find the probabilities of a continuous random variable, what can I do? Well, I can use something known as probability density function, also referred to as PDF. Now PDF will show me all the probabilities that the continuous random variable will take. Okay, again the notation is very simple. It's f of x, the small f of x, that is equal to the probability that x is equal to random variable x will take on a value x. Okay, so rather than writing this, I can write it as f of x. So these are the notations, because you will often see the f of x like this. So you have to understand that what do we mean by this? We are just saying the probability that the random variable x will take on a value x. Okay, now a related concept to both this PMF and the PDF is something known as the Cumulative Distribution Function, that is CDF. Over here we also have CDF for a continuous random variable. Now what do we mean by this? This shows the total probability or the cumulative probability of a random variable less than this particular value, which is x. Now I'm gonna show you an example, and the overall definition and the concept will be very much clear, but just understand for now that you see this is the small f of x. Okay, we denote it either to the PMF. If it is a discrete random variable, we can say the PMF. If it's a continuous random variable, the same of f of x is to denote for a PDF. But over here you will see something like the capital letter f of x. Okay, so this is to refer that we are talking about the CDF. Okay, so please make a note, the capital letter f of x, that's what we mean by that. The probability that the random variable x will take on a value less than or equal to x. Similarly, the capital letter f of x, that is equal to probability that the random variable x will take on a value less than or equal to x. So these are the notations that we will talk about. Okay, now let's get right into understanding these concepts. Okay, let's talk about the probability mass function. Now when do we use this PMF? For discrete random variable. Okay, when we have a discrete random variable which we can count, observe, it doesn't go into infinity, we can use the PMF. Okay, so over here I have this probability distribution table, and over here I have this visual representation. So how do we interpret this thing? So as you can observe, on the x-axis we have all the possible outcomes that the random variable can take. Okay, so this is an example of rolling a dice. So when I roll a dice, I can have 1, 2, 3, 4, 5 or 6. Okay, that's what we have it here on the x-axis. On the y-axis I have all the probabilities. As you can see, 16.6%, that's 0.5%, and finally up until the 1%, that is 100% of the probabilities. Now 1 divided by 6, that is 16.6. so rather than writing here as 1 by 6, I've taken the percentage value. So as you can observe, the probability of, let's say, getting a 3, okay, so probability that the random variable x will take on a value of 3, I can either see this table, okay, it's 1 by 6, or I can see here 3, it's 16.6, that is again 1 by 6. Now both these distributions are helpful and they both convey the same idea. So I can say that PMF, it shows me the total outcomes that the random variable can take along with the probabilities. I can say that, but I believe you must be wondering now, when we have something like this in a table format, why do we need this? Why do we need an additional stuff? Well, the reason for that is very simple. Now here we are rolling one dice. Okay, now just imagine if we have a portfolio of 1000 loans or maybe more than that. Can we write x is equal to 1, 2, 3, 4, so on and so forth up until those thousands, hundreds of thousands of customers or customer base, and along with their associated probabilities? That's going to be a very tedious job. So in order to replace this, we have these visual diagrams, so that with the help of some statistical software we can find, or we can find the PMF very easily. Alright, so they both convey the same idea, but this is more useful. So that's what do we mean by PMF. It shows the possible outcomes along with their probabilities. And to give you another example, I also have another example of tossing a coin. When you toss a coin, what are the possible values? Heads, tails, and as you can see over here on the x-axis we have the heads, we have the tails, and the associated probabilities as well. So this is again a PMF for a coin. Now one thing to note here is that when we're talking about these PMF, we need to make sure that whenever you calculate these 2 possible outcomes or these 6 possible outcomes, if you add all these 6 outcomes, okay, 16.6, you will have a value of 1, because we know that the maximum probability is 1 or 100%. Okay, similarly, if you add both the individual probabilities of heads or tails, that is 0.5 plus 0.5, that is equal to 1. Okay, so that is something that you need to remember. And I also have another example here. Now I've just made this up. Okay, so let's say, suppose that I'm a bank, and if I have hundreds or thousands of customers who have taken loan from us, and this is the probability of default. Now this is just a sample. If you add all these probabilities, they'll not sum up to 1, because there are multiple customers that goes on. I've not included that just to save some time and space. So this is just a sample that I've taken. By just having a visual look, I can say that the probability of default of A is 0.1, for B it's 0.3, so on and so forth. That's what we see here as well. Okay, so this is just another example so that you understand what do we mean by a PMF. Now something that we need to talk about, the cumulative distribution function, that is also related to the PMF as well as a PDF. Okay, so CDF is related to both the PMF as well as PDF, but here let's talk about PMF. So here I have the PMF of rolling dice, the same PMF that corresponds to this example. So as you can see, on the x-axis we have the possible outcomes, on the y-axis we have the probabilities. Now cumulative distribution, as the word says, it cumulates or accumulates the probabilities. Okay, one more thing that we need to talk about, and the PMF, we denote it by the small f of x. Okay, that's what we denote the PMF. What do we denote by the CDF? That is the capital letter F of x. Okay, that's what we mean by a PDF. So back to the example again, probability that the random variable x will take on a value less than or equal to x. So let's suppose that if I want to find the probability that x will take on value less than equal to, let's say if I want to find 4. Okay, so over here I can just, by having a visual look, I can say that okay, probability of 4 is equal to 66.5. that's what the value is. Now basically, to find this answer I can just have a look at the diagram. But if I don't have this diagram, essentially what we need to do is we need to add the probability of x is equal to 1 plus the probability of x is equal to 2 plus the probability of x equals 3 plus the probability that x equals 4, because see, we want to find the probability that x is less than or equal to 4. So we need all these 4 probabilities which is less than or equal to 4. So I can add this probability of 2, probability of 3 as well as 4. Once I add these probabilities, 16.66 plus probability of x is equal to 2 is again 16.66, so on and so forth. If I add this and this, I will have my answer as 66.65. Okay, so essentially what we have done is we have accumulated all the individual probability and we found a total probability, and that's what we mean by a CDF. Okay, so hopefully the concept is very much clear now. This is something that you will see something like this. The cumulative probability, it just keeps adding up. Okay, so if I want to find the cumulative probability of 5, I need to add 4, 3, 2, 1. Okay, that's something that I need to add to get the cumulative probability that the random variable x is less than or equal to 5. That's how I can go ahead and I can find that. Similarly, I can have an example of this coin toss. When I toss a coin, I can have heads or tails, and if I want to find the probability of the random variable x takes on value less than equal to tails, I can use this and I can have that it's gonna be 1, because 0.5 plus 0.5, that's going to be 1. And again, I can find this loan portfolio. If I want to find any specific value, I can go ahead and I can add that and I can find the CDF. Alright, now let's talk about PDF. Now when do we use PDF? When we have a continuous random variable. Okay, that is when we use PDF. If I have a discrete random variable, I'll use PMF. Okay, so that's the major difference. Now over here, what I have is a distribution, and as you can see, there is no specific value that I can find for a continuous random variable. So if I want to find a specific value, let's say out here, okay, now what is the value here? I'll not be able to find that, because for a continuous random variable, anything having a specific value, the probability of a specific value is 0 when we are talking about a continuous random variable. So how can we go ahead and we can find the probabilities? Well, with the help of this PDF, what we can do is we can find a range. Okay, within a range of values, I can go ahead and I can find the random variable. Okay, so if I want to find the value within this particular range right here, I can go ahead and I can find that. So this is the entire essence of the probability density function. Okay, now as you can see in this particular example, what we have is the returns on a particular company, and the negative 1% return, they are to the left of this distribution. So if I want to find this shaded region, okay, with some calculations that we will see in the next chapter, we can go ahead and we can find that it's 15.87. Blue shaded area, this entire thing below this negative 1% returns, that is 15.87%. Okay, so that's how I can use this PDF to find the probabilities for a continuous random variable. Alright, now I'm going to bring this CDF. As I said, CDF is related to both the PMF as well as the PDF. So over here I have the CDF of this same example that we see here, and it looks something like this. Okay, on the x-axis we have the returns over here, and on the y-axis we have the probabilities. Okay, so I can see with the help of CDS I can find this region to the left, and the probability is 15.8%. So what do we mean by CDF? That's the probability that the random variable x takes on a value less than or equal to x. Okay, so in our example, the probability that the random variable x is less than or equal to -1% return, that is this 0.1587, or I can say 15.87%. So this is the cumulative probability of random variable x taking a value less than equal to -1. Now I hope that the PMF, PDF, CDF, they are clear to you. Okay, learning objective 13b, understand and apply the concept of a mathematical expectation of a random variable. Now this expectation, or the expected value of a random variable, is a very important, and what it means is the weighted average of the possible outcomes of a random variable, where the weights are the probabilities that the outcomes will occur. Okay, so what exactly we mean by expectation? Basically, it's a method through which you can calculate the average value of a random variable. Okay, but the thing to note is that it's not a simple mean or a simple average. Okay, we have the probabilities that are associated with the random variable, and that's why we have this probability weighted formula. Okay, so here if you look at the expected value of a random variable formula, so it's written as this E of the random variable x. Okay, that's how we write as the expected value or the expectation. So what it simply says is that the expected value of a random variable x, that is equal to sum of all the outcomes that the random variable can take multiplied by their individual probabilities, and that is what we see here. The x1 is the outcome 1 of a random variable, x2 is the second outcome that the random variable, and then so on, x3, x4 and x5, so on until xn, and we have these individual probability of x1, probability of x2, so on and so forth until xn. So that's what we mean by this expected value formula. So the entire purpose of having the expected value of a random variable, we can actually make a best guess as to what will be the average value of a random variable. For example, of rolling a dice, and if I want to find the expected value, what will be the expected value of this random variable? So I can find the x1 as this outcome, which is 1, and the probability of x1 is 1 by 6. That's the probability, and I multiply this, plus I will have the x2, which is 2, and I will have my probability of x2, which is 1 divided by 6. Okay, so that's something my second outcome, so on and so forth until we reach to x1 multiplied by the probability which is the sixth. The x6 will be the outcome, which is 6. So if I go ahead and if I calculate that, I will have my expected value of the random variable as 3.5. Now technically speaking, you cannot have 3.5 when you roll a dice, but over a longer period of time, if you are rolling it once, twice, thrice, four times, 5 times, so on and so forth, ideally the average should be 3. Essentially, that is the entire purpose of the expected value. You can make a quick guess as to what could be the average value of a random variable. So let's take an example. The probability distribution of earnings per share, that is EPS, for a particular store is given in this following figure. Calculate the expected earnings per share, that is EPS. That's what we need to find. Here in this column we are given the probabilities, and we are also given the earnings per share in this particular column. So I can calculate the expected value of the earnings per share. That is going to be the probability of this, which is 0.1, that's the 10%, multiplied by the x1, which is 1.80, plus the second outcome is 0.2 multiplied by 1.60, plus the third outcome, that's 0.4 multiplied by 1.20, plus 0.3, that's 30%, multiplied by this £1. Okay, so once we go ahead and if we solve that, we will have the answer as 1.28 pounds. Okay, so this is the best guess that we can make with the help of these probabilities and the earnings per share. So this is the expected value of the EPS. Okay, so that's how we can go ahead and we can find the expected values. Okay, moving on to the next learning objective, describe the 4 common population moments. But what exactly are moments? Population moments, they help us to measure the distribution with the help of some statistical parameters. Okay, now that's just the definition, but what do we mean by that is, let's say we have our data. Now how can we know about the shape of the data? What is the average of that particular data? Okay, the data can range from, let's say, 10 to maybe 100. So what's going to be the average or the center value of that particular data? How the random variable will look like. So on and so forth. With the help of the population moments, we can go ahead and we can describe the features of a random variable. Okay, so let's just suppose this is how our data looks like, and in the center of this distribution we have this mean or mu. Okay, this is also referred to as mu. Okay, so this Greek symbol is referred to as mu. Okay, so let's first talk about the first population moment, and that is the mean. Now as we have seen in this data, the mean or the mu is the average of the random variable. Now we have already talked about the expected value of the random variable, okay, in the last slide. So that's just the mean that we have here. So that is our first population moment. With the help of mean, we can calculate the center value of our data. Second central moment that we have is referred to as variance. Now this is the second moment, and it measures how closely the values are spread out around the mean. So if, for example, if this is the mean, how the values are spread out in our distribution, that's what we that's what we can understand with the help of the variance. Okay, the formula of the variance, it looks like this. Okay, so this is the symbol for variance, and that is the expected value of the random variable x minus the expected value of the x. Now over here, the expected value, we have it as the mu, right? That's the center. So I can just replace this thing here, so it becomes the expected value of x minus the mu squared. Now the reason we square it because it ensures that the variance is a positive number and not a negative number. Okay, we're going to be solving some questions in the later chapters, but just for now, for this particular chapter, understand the first moment is mean, the second moment is variance, and we just take the difference from the mean. Okay, the expected value of the random variable, okay, random variable minus the mean, and we square it and we get our variance of this distribution. All right, the third moment is referred to as skewness. Now skewness, it talks about the shape of the distribution. What is the shape of your particular distribution, how it looks like. Skewness will help you identify that. So this is a measure of the distribution's symmetry and is the standardized third moment. Okay, this is the formula of skewness, the expected value of x minus the expected value or the minus mean. That's what we have, and we cube it. We have this cube here because this is the third moment, okay? And we can standardize this skewness formula by the standard deviation cubed, okay? So this is another thing that we have. We're going to be taking an example on how to calculate this skewness, so but just for now, understand this is the third moment and we cube it, okay? Now, to understand skewness in a much better way, I have these three diagrams, but consider this the distribution that we have here. 50% of the data is on the side, and over here we have the same amount of 50% data. So I can say that this distribution is symmetrical in nature, and the skewness for this particular distribution is 0, okay? The data is not skewed at all. That's what we see here. On the contrast, imagine we have a negative skewed distribution. Now, what do we mean by this? If you can see, there's a lot of data on the left hand side, on the negative side of this distribution, okay? And as you can see, the tail is just going over here. So there's a lot of data points in the negative side on the left side of the distribution. So we call this as a negative skewed distribution or left skewed distribution as well, okay? Similarly, we have a positive skewed data that, for example, a lot of data points are on the positive side of the distribution. So we can say that this is a positive skewed distribution or a right skewed distribution. Now, skewness as a measure is very important, because understand, as a risk manager, I want to have positive returns, okay? I want to have as much positive returns as possible. Imagine a risk manager is having negatively skewed returns. That means a lot of data is on the negative side of a distribution. So this reflects losses, right? That is why skewness as a measure is very important for risk management. So after skewness, the last moment, the fourth moment that we have is kurtosis. Now, we've talked about the skewness, whether the distribution is skewed to the left or it's skewed to the right. Where exactly is the tail? We can go ahead and we can find that. But what if I want to find, let's say, if the distribution is it more peaked? Is it less peaked? So when we think about kurtosis, remember that we're talking about the peakedness of a distribution, okay? So kurtosis, it also measures the shape of the distribution, just like skewness. It measures the extent to which a distribution is more or less peaked than a normal distribution. So as you can see, this blue shaded is the normal distribution, and these dotted lines, okay, this particular distribution, this is more peaked than the normal distribution. So that's how we can measure the peakedness of the distribution with the help of kurtosis. So usually the normal distribution has a kurtosis of 3, okay? This is something that you need to remember, that the normal distribution kurtosis is 3, all right? And the formula to calculate the kurtosis is this: the expected value of the random variable minus the mean to the power 4. Now this is the fourth moment, so we have the 4 here. That's one way that you can remember it, but it usually talks about the outliers, okay? The wider the outliers, as you can see, the more data on both the negative as well as the positive side, there's a lot of so this suggests that there's a lot of outliers. It has also fatter tails than the normal distribution, okay? You're gonna see a lot about the fat tails, okay? So essentially, fat tails means there's a lot of data on either this side or this side, or probably both, okay? And that's something not good as well. On the positive side, that's good. That means you're generating good amount of returns. But on the negative side, that's a poor sign, okay? So that's what we mean by kurtosis. We want to standardize this kurtosis measure. We can divide it by the standard deviation to the power 4, okay, and we can find the answer. Now suppose let's say that you used this particular formula and you found the kurtosis to be, let's say, 2.5. okay, so there's this concept known as excess kurtosis. What do we mean by that? Okay, so this is a measure that you can use to find how much is the excess kurtosis. So over here we got the answer as 2.5 and minus the normal distribution kurtosis is 3. Okay, so this 0.5, this is the excess kurtosis when we compare it to a normal distribution. Okay, so this is also one important metric that can be used. Okay, the skewness, kurtosis, the mean, variance, all these things, they are part of a later chapter. Well, and there are many calculations that are involved, so we're going to be calculating these measures as well. Okay, moving on to the next learning objective, characterize the quantile function and quantile based estimators. Well, when we talk about quantile function, it's nothing but the inverse of the CDF. Okay, for example, and this is how we denote the quantile function. So let's take that we have this distribution and we want to find the CDF. Okay, so that's going to be the probability that the x is less than or equal to 2. Okay, we have got the 2 and we want to find this probability. Okay, and the answer we have over here is 30%. Okay, so what CDF it tells us is that the random variable x is less than or equal to 2, that is 30%. But on the other hand, let's suppose that we have the 30%. We know the probability at first. Okay, we know that 30% of the area is to the left, but what is the value of this x? We don't know the value of x, or we want to find that maybe. So we can find with the help of quantile function. Okay, and that the answer will be 2. The quantile function is nothing but the inverse of the CDF. The CDF will give me the value of the probability, which is 30%, and in quantile function we include the probability and we find the value of the x. Okay, just like what we have here. So that's what we mean by a quantile function. Now, two important quantile function that we need to talk about. The very first one is the median and the second one is the interquartile range. So median, it divides the entire series into 2 equal half. Okay, so as an example, I have this distribution, so I can divide this distribution into these 2 equal parts. Okay, so there's this 50% of the data is on to the left of the distribution and the other 50% we have to the right of the distribution. So that's the job of a median. Okay, so that's what we have as a median. It divides the entire series into 2 equal parts. Interesting to note, within this particular distribution, the normal distribution that we have is the median as well as the mean, they both are the same for this particular distribution. Okay, to understand the interquartile range, okay, it's the upper value and the lower value of the outcomes of a random variable that include the middle 50% of its probability distribution. Okay, let's understand this thing with the help of an example. So over here I've got the scores of the FRM level 1 exam. Okay, I've just made these numbers, they are hypothetical. So let's just assume the candidate who scored the lowest, he got 35 marks in the FRM level 1 exam, and the candidate who scored the highest, the highest marks was 72. Okay, so these are total 18 data points. Okay, these are the series is of 18 numbers. So what I've done is that the very first step in order to calculate this interquartile range is to first divide the entire distribution into 2 equal parts. Okay, that's why I have this purple line over here. So here we have the 9 data points, and over here on the right side we have 9 data points. Then further, what I did is, out of these 9 data points, I again divided this into 2 equal parts. Okay, so this 48 is the midpoint over here, and on the right side we have divided into two equal parts, and the 66 is the midpoint over here. So now the entire data set is divided into 4 equal parts. This is the first part, this is the second quarter, this is the third quarter, and this is the fourth quarter. So I can write it this way, that this one is the Q25%. What do we mean by this? The 25% of the observations are below this number, okay, below this 48. 25% of the observations are below them, and I can write it here as 75%. Okay, this means 75% of the observations are below 66. As you can see, 75% of the students are below this midpoint over here. So now to calculate the interquartile range, we have to understand that this range is a mathematical concept, which means the difference between two values. I have these two interquartiles, and the difference between two will be my interquartile range. So I have done the calculation over here. So IQR is the quarter, which is the third quarter over here, minus the first quarter. Okay, so that's the upper value, and the lower value, that includes the middle 50% of the distribution. Now as you can see, if this entire data set is 100%, then I've got this 50% of the data in the middle. So once I calculate 66 minus 48, I will have 18 as my answer. Okay, now what does this 18 means? Why are we actually why do we need the interquartile range in the very first place? Well, if you want to understand how data is either spread out or clustered around the median over here, that's when we use this IQR. Okay, we don't have to calculate this on the exam, that's not going to be the purpose, but I'm just showing you that if the answer is very large, that means the data points are they are very much spread out around the mean. Okay, they are very far away from the median, and if this number is very small, then the data points are very much clustered around the median. That's the entire purpose of this IQR. Okay, finally the last learning objective: explain the effect of a linear transformation of a random variable. Now before we explain you the effect of linear transformation, let's first understand what do we mean by linear transformation. So when we want to check the effect of one random variable x on another random variable y, we use linear transformation. So for example, here I have this equation which can describe the linear transformation. So over here we have this random variable x and a. Okay, now the a and b, they both are constant. Okay, so if we add something to the random variable and we also multiply this b to the particular random variable, what's going to be the outcome on another random variable y? So that is something that we're going to be talking about in this learning objective. Okay, the effect of adding and scaling the random variable and checking the effect on the other one. That's the entire purpose of linear transformation. To give you a simple example of a linear transformation, let's just say that we have this particular equation. Okay, now here I've taken the a as 2 and b is 1.5. okay, they both are constant, they remain the same. The return on the market is, let's say, 3%. So with the help of linear transformation, I can go ahead and I can calculate the return on this ABC company. Okay, so that is the entire purpose of linear transformation. Okay, talking about the effects of linear transformation now, let's just suppose that I have this random variable. Okay, this is x, and what I'm doing is I'm just adding a constant a to this random variable x. Once I add something to the x, I will have a new distribution which is this blue shaded. Now by having a visual look at both the distribution, I can go ahead and I can say that adding a constant to the random variable, the mean has shifted, right? When you add something to x, okay, which is a, the mean has shifted by the same amount. Okay, so I can write it this way: the mean of y, the expected value of y, is going to be the expected value of x, whatever the expected value of x, plus this constant a. And talking about the variance of y, okay, is there any effect on the variance? See, initially we had this much of variance, but the new random variable, which is y, the effect is the same. So I can say that there is no effect on the variance, they both are the same. So no effect on the variance when we add a particular constant to a random variable. Now we're going to be talking about the effect of scaling a particular random variable. So this b is a constant again, and I'm just multiplying this to the original random variable. So what's going to happen? Let's check it out. Alright, so this is our new random variable in blue shaded. Once we scale this new random variable y, the original random variable is stretched out. Okay, as you can see visually, this new one is pretty much stretched out, and I can say that the expected value of y, or the mean of y, scale factor multiplied by the expected value of x. Okay, so as you can see, the mean is shifted by how much? By this b. How much we are, if the b is 2, then the mean is shifted by 2. That's what we can see visually. Okay, so that's how we can derive the mean. Talking about the variance of y, okay, as you can see, if this is the initial variance, and if we stretch it out, we scale it by b, the variance has almost doubled. Right, as you can see the distance, it's almost doubled. So the variance of y, if we scale it by b, it's gonna be the b squared, that's the double of the original random variable, multiplied by the variance of x. You have the variance of x over here, and this is the variance of y. Okay, now let's talk about the effects on the mean, variance, skewness, and kurtosis, the effect of linear transformation on these variables. So the effect on the mean of y is the expected value of y, that is equal to a, which is the shifting factor, the b is the scale factor, multiplied by the expected value of the x. That's what we have seen over here as well as here. Right, so the variance of y, as we see, the variance is not affected by the shifting, it's only affected by the scaling. That's what we have seen over here. So if I want to calculate the variance of y, this new distribution, I just need to have the variance of x multiplied by the square of this scaling factor. The skewness and kurtosis. Now have a look at both these, the distributions of y. Do you see any distribution that is skewed to the left, to the right? No. So I can say that linear transformation does not have any effect on the skewness of y. The only thing that you need to remember is the skewness of y will have a negative sign when the b is less than 0, because if b is a negative number, then the skewness of x will be negative. So okay, so this is something that you need to remember. And finally, visually looking at the kurtosis, you can say that the kurtosis is also same. The distribution, it did not turn out to be peaked, less peaked, so on and so forth. Okay, so there's no effect on kurtosis as well. Alright, so with this we are done with the particular chapter.